representation of artifacts. But there are other types of artifacts. The second type of artifact is structured noise. So noise is not necessarily random, or you can call it structured artifact. There could be some patterns that appear, such as the X-ray grid artifact. If you go through the first chapter, you will see that in obtaining X-ray images, in between the patient and the detector, there is a grid made of metal strips with some insulation in between. And the grid pattern is there to minimize the passage of scattered radiation. Scattered radiation will hit the grids and will be absorbed there and not hit the detector. But the grid has to move, otherwise it will cast a shadow which will be parallel lines. So the grid is oscillated or translated during the period of exposure. But if there is a problem in that process of movement of the grid, if it starts late or ends soon, or if it doesn't move at all, then you get the X-ray grid artifact. You may use other grids and frames for image registration. I want to take your picture and then I want to register it with some coordinates, or have relative coordinate system within the image with reference to my markers. Labels indicating patient position left, right, and this and that. Craniocaudal view in mammogram, CC, MLO, left, right, and so on. They're supposed to be away from the patient, away from the part of the body being imaged, but sometimes they get too close. And in the projected image, they may fuse or they may connect. They may not connect in the actual situation of the patient and the labels being placed, but in the image, due to the angle of projection, they may touch. Surgical implants such as staples, pins, and screws, if the patient has had some procedure to fix bones, then they're there. You can't do anything about it, they'll be there in the image. Power line interference is common in biomedical signals, ECG and so on, but in images you don't encounter such noise. I have not seen that. There is not a straightforward way for power signal to interfere with your image signal. But maybe there are some situations where that happens. And then there is physiological interference. What I would like to call physiological interference is some artifact caused by physiological events within the body over which the patient doesn't have control, such as effect of breathing. We do have control on breathing. If it is an adult patient in good condition, you can ask, take a deep breath and hold until I take a picture. But with an infant, it's not possible. With an adult who is not in a good health situation, that is not possible either. Effect of breathing, peristalsis, movement of material through the gastrointestinal system, effect of cardiovascular activity on various types of images, CT, MR, effect of pulsatile movement of arteries in digital subtraction angiography. When you want to take an image of the blood vessels in the brain, then with the digital subtraction angiography, you take, I'll show you that later on, a reference image and then the live image and subtract. But then the blood vessels will be moving due to pulsatile movement of the blood, and that causes artifacts. So these are physiological. They're not random. They're not structured in the sense there is no geometric fixed structure. There is a structure for the patient, for each subject, depending upon the imaging situation, but you cannot model that. So anatomical details such as the ribs in chest X-ray images and the skull in brain imaging and the pectoral muscle in mammograms, they are not of interest. You want to analyze something else, but they are there. So you may want to remove them using image processing segmentation operations. They're not noise, they're normal, but you're not interested in them. You want something else. So those are also parts of the image in which you do not have an interest, and hence you may say it is an artifact. But you can't escape. There could be geometric distortion, miscalibration, nonlinear response of detectors, sampling and quantization we saw. All of these affect the quality of the images. And then a few more. Punctate or short noise due to dust on screen film or on the examination table. There could be some dust or the patient may have some cosmetic powder or something, and those are high-density specks. Scratches on film, if you scan film and if there is a scratch, but again, we don't do that anymore. Short noise due to inactive elements in a detector array. This happens in your camera, but it is automatically corrected in your camera, so you won't see it. But in medical imaging devices, if you take that CCD, which is not programmed to correct for this, then you may see a few dead spots. Salt and pepper noise due to impulsive noise. Salt is bright and pepper is black, inactive element, or one that is saturated and left there. Film grain noise due to scanning films with high resolution. You may get patterns of the grain, the silver halide grain crystals, on top of the image details. So that is film grain noise. Punctate noise in chest X-ray or mammograms caused by cosmetic powder or deodorants that may appear to be calcifications. You don't want to mislead diagnosis by these. So the instructions before such imaging procedures tell the patient, do this and remove this and don't use this and so on. But sometimes they do happen. Superimposed images of clothing accessories such as pins, hooks, usually they don't happen, but they do happen in practice. There are cases of people walking into an MR scanner with metallic implements, with metallic objects, and that's extremely dangerous because they could fly and hit somebody in between or get ripped out of the body too. There are scanners to prevent this, but they still happen. To characterize artifact, we have a couple of methods and techniques. You characterize them as stationary or non-stationary to begin with. Random processes may be characterized in terms of all of these statistics we saw, temporal, spatial, ensemble. A process is said to be stationary in the strict sense or strongly stationary if all of its statistics are not affected by a shift in the origin or time or space. So if you take a bunch of samples here or there, if the statistics are the same, all statistics, all moments. In practical applications, only the first and second order averages like mean and standard deviation or variance are used. And then it is said to be, if those are not changing with a shift in time or space, then the process is called weakly stationary or stationary in the wide sense. If the mean is constant and the autocorrelation depends only upon the difference or shift in time or space. So mu f x1 y1 is simply mu f. It does not depend on x and y. And phi x x1 plus alpha and all that is only phi alpha beta. So there is no x and y coordinates in these. So the autocorrelation function is a function of the shift parameters alpha beta only, and the path spectral density does not vary with space. So I can characterize the entire image with one power spectral density. But that's not true. In the case of a chest X-ray image, we have ribs here, we have the heart here, and we have other parts where they are smooth, and so the characteristics are different from one portion to another. So to assume one spectrum for the entire image is in the average sense, but it doesn't apply to various parts individually, even in one image, such as a chest X-ray image. So these characteristics are in general spatially varying. A stationary process is said to be ergodic if the temporal statistics computed are independent of the sample observed. I take one signal here, another signal there, another signal at some other time, and if the statistics are the same, then you say temporal statistics from each one. Then you assume the process is said to be ergodic, and then you can use the time averages instead of the ensemble averages. Collecting an ensemble of signals takes time, and there could be some expense. And there are issues with patient movement and so on. So if you can do temporal averages with one signal, it's simpler. For that, you have to make the assumption of ergodicity. Yeah. In the case of a signal where statistics vary with time and space, it is said to be non-stationary. The statistics of most images vary over space. Only a flat image like this, there is no variation. But even here, these are flat areas, there is something here, and the shape changes, the color changes. So the characteristics change over space. If there is no change, then perhaps there is not much information in the image. It is that variability that gives you the pictorial information. So biomedical systems are dynamic and produce non-stationary signals and images. In the case of heart sounds, you have the first sound, the lub-dub, the first heart sound, second heart sound. There could be murmurs in between, some whooshing, swishing sounds in between, with blood going through some constricted space. Then there is high-frequency noise. Low-frequency first heart sound, high-frequency noise. A little medium-frequency second heart sound, maybe low-frequency diastolic murmur. So the spectral characteristics change within one cardiac cycle. Over every 20, 30 milliseconds, the spectrum changes. The same in images, things change. So most of the images we see are non-stationary because the systems generating them are dynamic. They are varying with time. A physical or physiological system has some limitations though. The heart rate can only be so much, maybe up to 250 or so. So if you take smaller divisions of time, you can assume the signal is stationary within that small interval. Or you have a big image, you know this part is, there is nothing, and this part there is something else there. So you can break into parts and say each of these parts is stationary. So this facilitates the breaking of a signal into segments of short duration. And then you assume each of those to be stationary. You call it quasi-stationary, almost stationary. There is variation overall, but within small sections, it is stationary. This is commonly done in speech signal processing using what is called short-time signal processing. You don't take an entire speech of several minutes and analyze in one shot. That's not possible. You take short pieces, short-time analysis. Within those short windows, you assume the signal has the same spectrum, same autocorrelation. It is stationary. So that is then the notion of quasi-stationary processes. So we have this idea of short-time analysis, or in the case of images, block-wise or sectioned processing. I process this and this and this separately. For each block, we assume the image to be block-wise stationary instead of calling it short-time processing. So section, block by block, moving average, moving window processing techniques may be used. So you don't process the whole thing in one shot, but little windows, and the window is moved around. There is another special case in biomedical signals known as cyclostationarity. Stationary, yes, but not within one cycle, but from one cycle to another cycle. The same part, the same phase of the cycle will have similar characteristics. The first heart sound from this heartbeat to the next heartbeat to the next will almost be the same. There will be the effect of respiration. As my lungs expand, my chest expands, the transmittivity between the heart and the exterior microphone you put there, the intervening medium will change. So there will be some variation. But if you go within the heart, quite likely, if you put a microphone within the heart, you can do that. Not you, but trained people can do that. Then it is possible that those successive heart sounds, first heart sound is the same, second is the same. The murmur is random, so there could be variations. Then it's called cyclostationary. It is a cyclic or cyclic process. The same thing happens every cycle or every beat. The heart rate could change, so you use the ECG as a trigger and say this much and that much from the next beat and that much should be the same. Then you can average, create an ensemble of those pieces and average them, which we do in that book you saw. in biomedical signal processing to average across multiple observations of the first heart sound only, second heart sound only, over multiple cardiac cycles using the ECG as a trigger. Or similarly, you have other applications where one signal is used as a trigger and another signal is acquired and averaged in an ensemble. So cyclostationarity helps in creating an ensemble of a signal that really is continuous, but you're breaking into parts and synchronizing them. In gated blood pool imaging, nuclear medicine images of the heart are acquired in several parts over short intervals of time. If you take a picture in nuclear medicine imaging, a radio isotope is injected and it is tagged so that it goes to a particular part of the body, such as the left ventricle, and then you take pictures. But to take a picture, it takes several seconds. The gamma camera needs to count photons over a few seconds. But over a few seconds, the heart has gone through multiple changes depending on the heart rate. So this averaging or counting of photons over a long period of time cannot be done continuously. So you take the ECG and find the QRS complex, the beginning of the beat, and then break each cycle into parts. And for each phase of the cardiac cycle, you gather the counts and make an image. But that image is not useful because you don't have enough counts. There'll be too much noise. So the next window you put in the next frame, and maybe you take 8 or 10 frames per cardiac cycle. And when the next first heart sound comes or the QRS complex comes, you put that to the first frame, second frame, and so on. So this is called gated imaging, using the ECG as a gate. So this takes to benefit cyclostationarity. Otherwise, it's not possible to get a picture of the heart using an imaging system that requires counting of photons over several seconds. The covariance and cross-correlation are two more measures. We saw autocorrelation. In cross-correlation, the signals are different, not just the same. In terms of the expectation value, the sigma value is expectation of f minus mu f times g minus mu g. Previously, it was f minus mu square. So now you have two functions, two images, f and g, their means, and multiply with the joint PDF and integrate on both of them. So you need the joint PDF of the two processes. Covariance is normalized, sigma fg over sigma f sigma g, and then it is between plus and minus 1. High covariance indicates that the two processes have similar statistical variability or behavior. Not that they are identical, but similar variability. And they're uncorrelated if rho fg is 0. The statistical independent processes are also uncorrelated. The cross-correlation function is expectation of fxy with g, x plus alpha, y plus beta. So you apply a shift to one of them. So this facilitates analyzing the nature of variability and also template matching. I have a template of something I want to detect, and I expect it to be present in the image, but I don't know where it is. So I create an image of this, and then I go like this, multiplying and integrating over this space and with a shift. And when a large value is found, then I have found that object. That is used in radar in 1D signal processing to detect return signals you get from a signal that you send out, an echo, and that's template matching, which is related to cross-correlation. I mentioned earlier that we typically assume noise to be independent of the signal, but there are situations where, in imaging especially, noise is dependent upon the characteristics of the signals or the value of the signal, so you cannot treat them as uncorrelated. The noise is functionally related to or dependent upon the signal. And how you define that, for example, for some noise, I gave you one expression earlier. Here is another expression. The probability of occurrence of a certain value G0 Mn is dependent upon Fmn, the original signal, and some factor lambda. And you don't need to remember this, but the probability of occurrence of this value G is dependent on the original value F in this relationship. There is some exponential factor, but this is raised to the power of G0 Mn, G factorial, like K factorial we had earlier. So this shows that the PDF depends on the signal and some factor, the PDF of this value being observed. So Poisson noise is one case where it is signal dependent. So the expectation of G0 Mn, it turns out to be lambda expectation of Fmn. And normalization is done this way. Gmn is G0 over lambda. That facilitates some analysis. So with some normalization, you may convert signal-dependent noise to signal-independent noise, and then your further analysis is simplified a little bit. So Poisson noise may be modeled as stationary additive noise in this manner if you take sigma eta square to be expectation of Fmn over lambda. This lambda factor provides that, facilitates that assumption. Film grain noise is often encountered not only in medical applications but other applications in aerial photogrammetry and so on, where film used to be used. Nowadays, most of it is digital, but there are still some high-resolution imaging applications where film could be used. And when you scan film to high resolution using some imaging device, laser or CCD, you encounter film grain noise. The granular structure of film due to the silver halide grains contributes to this noise. The structure of the film itself, which is not uniform at the level of the resolution you'd scan. If you use poor resolution, you may not encounter that. So there is a model given by this equation. Gmn is Fmn, the original signal, plus this factor. Now this factor, kappa is some scale factor. This script f is some function of Fmn, of the original signal, which you don't know, of course, times eta 1, multiplicative noise, plus eta 2, additive noise. So this is a general model which includes both multiplicative and additive. And if you assume kappa is 0, then it's only additive. But you need to have some idea of what this function is. And yeah, I already mentioned that. One of the assumptions is to use a square root, Fmn to the power of p, with p equal to 0.5, so it's square root. That's a commonly used model. So kappa square root Fmn times eta 1, multiplicative and signal dependent. So this causes some complications. There is a model given where film grain noise may be modeled as additive noise, eta mn kappa square root, that's a function dependence, eta 1 plus eta 2. That's what is given in this model. And the mean and variance are given by this equation. Again, you don't need to remember that, but if you need to, you can refer to that. In synthetic aperture radar, speckle noise is encountered, which is again multiplicative. Gmn is Fmn times eta 1. The distribution in this case is typically not Gaussian. It could be exponential or Rayleigh or Gaussian sometimes. The multiplicative model may be converted to an additive model to facilitate further processing by modeling the variance in this manner, where you have sigma square g, the variance of the observed signal, its mean square, and this ratio sigma square eta 1. And that is the space variant signal dependent variance. Mn indicates it is space variant. So there are some transformations and manipulations of this nature which help in converting signal dependent noise into some other type of noise that facilitates further processing. So there are a few papers where this kind of a transformation has been applied. TGM is alpha square root GMN. So that is normalizing, alpha is a normalizing constant. And the noise in the transformed image is additive, has a Gaussian distribution, and so on. Okay, so I quickly went through some of that. Now, how do you apply some of these concepts to get better images, filter noise, and achieve reduction of artifacts? So let's look at some procedures and examples. The first one I mentioned is synchronize or multi-frame averaging. I take a number of pictures of the same scene, assuming no change, no motion change, no change at all in the structure, except for noise. Then average. Noise will be reduced by averaging. So this is known as multi-frame averaging, or synchronize, because you have to synchronize your image acquisition with something. If there is variation, such as ECG, you can use that and synchronize acquisition to that. But if nothing is changing, then simply take multiple images. If an object can remain free from motion, internal or external, over a certain period, then you can acquire several frames of images of the object. Then you average them, known as multi-frame averaging. So as I mentioned, if there is variation, if there is a trigger that can help you in identifying the same phase of the activity, such as the ECG, doesn't have to be periodic. The ECG is not perfectly periodic, but a trigger helps in identifying where something is happening. And you take portions of the signal synchronized to that activity. So then it is synchronized averaging, and it is a kind of ensemble averaging. You're getting ensembles of images taken at a certain instant in a situation which is changing, but the same thing is happening repeatedly. So the cardiac system, whose phases of contraction are indicated by the ECG signal, facilitates such acquisition of images in nuclear medicine imaging. So the model is very simple. GIXY is FXY plus eta IXY. FXY, the original, is the same. GI is the ith acquired image. Eta I is noise in the ith image. But you may assume the noise is the same from one image to another. So the same noise is happening. So assume that the noise is independent of the signal. The original image FXY is the same. Then it follows that the variance of GI is equal to variance of the noise only, because the signal is fixed. FXY has no variance. If m frames are acquired, G bar xy is 1 over m, I going 1 to m, Gi xy, just adding all the frames and dividing by m. If the mean of the noise is 0, then mean of the noise will tend to 0. The average of the noise, the 1 over m, if you want, the average will tend to 0 as m tends to infinity, or is large. Then expectation of G bar is equal to f, the original image. And you can show that the variance of sigma square of G bar is 1 over m variance of noise. So the variance of the observed image reduces with the number of images that you are acquiring and averaging. So the variance is reduced by a factor of m. The SNR is improved by a factor of square root of m, because you're using the variance here. So motion or change between the frames will lead to distortion. If I take a number of images, if somebody moves, then there is some blurring or something happens, which will cause distortion. But in the absence of that, you will get an improvement in SNR, signal to noise ratio, by a factor of square root of m. This is just a synthesized example. We created a number of test patterns like this by randomly placing various shapes with various gray levels and then adding noise. So this is the original image with noise. This is with noise, Gaussian noise added, And this is another version with Gaussian noise added. Not exactly the same, but different noise samples added to the original. And results of multi-frame averaging using 2 frames. If you average these 2, then noise is reduced to some extent. But if you average 4 frames or 8 frames, you get a smoother result without blurring of edges. So you can take this and zoom and look at the details later if you wish. So the more the frames you average, the better the signal to noise ratio. I'll show the nuclear medicine example later towards the end of this chapter. I placed some examples at the end of the chapter as applications. Space domain operations using local statistics, like temporal moving window averaging of 1-day signals. If you don't have an ensemble of images to do multi-frame averaging, given only one image, you average over space using a local window. So given a single noisy observation of image of some finite size, we do not have any access to an ensemble of images, and you may not even know the PDF of the image. So spatial statistics are computed over the image. But if you do that over the entire image, that doesn't help. You get one value, and that doesn't help. So we should accommodate for non-stationarity of the image too. So then you go for local statistics. A moving window filter uses windows of small size, typically squares 3 by 3, 5 by 5, 7 by 7, but later on I'll show other types of windows. Rectangular windows as well as windows of other shapes may be considered when appropriate and when you can design something for the specific application. So all you do is say, okay, there is a position here, I'll take that window and process it and put it at that location. Next I take that position and take that window and do something and put it at that location in the output, and for every pixel. So that's fairly simple. So this is a moving window over the entire image, and at the center of the window, you position that window at some location, and you compute statistics or do some operation on the pixels within the window, and apply that result in the output image at the location of the center of the window. Note that only pixel values in the input image are used. The output is in a separate array. There are different shapes of windows that one could use and that have been recommended in some books and research papers. It depends on what kind of artifacts are caused by the windows and which kinds of artifacts are acceptable and which are not. So the common one is 3 by 3, all right? It's also called 8 connected. There are 8 neighbors to this pixel. If you don't want to take the corner, because the distance from here to the one above and to the left and right and bottom, that's 1 pixel distance, but this distance is square root of 2. So it's not the same distance. So you may say, no, I don't want the corner, I'll take only 4 connected or integer distance 1. Then you get that shape. A vertical bar, horizontal bar, a bigger square, and if you trim the corners, you may call that a circle, approximate circle, a cross, bars, again, longer bars, and some other shapes. It all depends on what kinds of patterns exist in the input image and how they are distorted by these filters. There will be distortion. And which patterns are of interest in the application to the end user, and how to prevent artifacts that will not be suitable in the application. The mean filter is simply taking the average. But there are assumptions. The image component is relatively constant, that is quasi-stationary. We assume that within the window you're using, the image is stationary. If I put a small window here, okay, that is stationary. I move, I come here, but then this thing got inside my window. Now it's not stationary anymore. But I still assume it is stationary. When I average, that gets blurred. The value of this is spread over. As I move the window, this comes in, and again, not stationary. So that's where the method fails. All methods work to some extent in some applications, and they have limitations. So one must be aware of the limitations. The only variations in the neighborhood are due to noise. That is, all the pixels in that window are related to the signal at that location, and the variation among them is only due to noise. So by averaging, noise is reduced. Noise is additive, noise is independent of the image or signal, and noise has zero mean. These are the assumptions made. The 3 by 3 we saw earlier, this is the current pixel, and you take the neighbors and just average them. We saw the convolution mask also, which is this. So this procedure is convolution. It's a linear process. It's a linear shift invariant process. The same thing is done everywhere. And the point spread function, or the impulse response, is that. There is a problem at the edges, because when the image ends here and you want to put the mask here, centered at that pixel, you don't have anything outside the edge. So what do you do then? You may say, well, I don't process it. If you put 0, then output will have a border. If you put the same values, then there'll be noise there. So you may say, well, for this point, I have these neighbors. I'll use only those neighbors, 1/2 of the window, and process. So that'll give you perhaps a passable result. So you may extend the input with a border of 0 valued pixels, which is effectively what I said. Or you do not process, but that leaves noise. Replace edge pixels with an average of available neighbors, which may be a better option. The mean filter can suppress Gaussian and uniformly distributed noise effectively in relatively homogeneous areas like this, or within these characters. But when you come across, when you change from when the window overlaps background and object, then there is blurring. So the operation leads to blurring at edges of the objects in the image and loss of fine details and texture. So fine detail like this dot will be blurred out. Blurring of edges can be minimized by not applying the mean filter if the difference between the pixel and the mean of the neighbors is greater than a threshold. So when you come here, when the window is sitting here, you say, oh, this pixel and its average of the neighbors, the difference is large, so I will not process it. We'll leave it like that. Then it becomes nonlinear. You put conditions, then the filter is no longer linear. The median filter may do better. The median is a sample that splits the value of the population you have in half. So you have a bunch of pixel values from a neighborhood, 3 by 3, 5 by 5, whatever, and you take the value in the middle of that distribution so that there are half the number of pixels on one side and half on the other side. That's the median. This is typically done using a rank ordering process. It's not necessary to rank order all of them, but you can do that. You use an odd number of pixels in the neighborhood, like 3 by 3, 5 by 5, so that you can find the pixel in the middle of the distribution. So the value at the middle of that list is, after rank ordering, the middle value is selected. It's a nonlinear filter, but it can reduce noise without causing blurring. But there are some other problems which I'll illustrate. So it provides for better noise removal than the mean without blurring, especially when the noise has a long-tailed PDF, resulting in outliers or salt and pepper noise. If you average salt and pepper noise using a mean filter, you get blotches at every location of the salt and pepper noise. But the median filter could result in clipping of corners and some distortion of shape, especially if you have strong edges, then there will be distortion of shapes. And median filtering with large neighborhoods could result in the complete elimination of very small objects, such as a little dot. That'll go away when you apply a median filter. Non-square neighborhoods, like the other shapes I showed, they are used typically in median filtering to avoid distortion of shape. So here's a simple example with a 1D signal, just a block here, a rectangle, and I added some spike noise, salt and pepper noise to that. And if we apply the mean, you get this, which is not very good. The mean filter was applied with n equal to 3 samples. If you apply the median, you get the original back. But this is a synthesized example, a made-up example, but it shows how median is better than mean in such cases. But here we have uniformly distributed noise. The original, I added this spike, a small rectangle and a big rectangle. Let me not call it a spike, with uniformly distributed noise added here. The mean filter and the median. The median filter has suppressed this small pulse. Was that a pulse of interest or was that noise? I don't know. I cannot tell. So if you believe that is a signal of interest, then this is not good. But look at the edge here. The mean filter has blurred the edge. The median filter maintains the edge. This is blurred, this is straight and sharp. So in most cases, the median filter does a good job. But the question is, what kind of a neighborhood you want to use and how many samples to compute the median. The root mean square error or mean squared error, MAC, they are used to compare results of various image processing systems. If you have a test image, you can take the distance between the test image and the various filtered images, or the noisy images and the filter images. You need some reference. An image with a higher RMS error may present visual better quality than another with a lower RMS error. Several studies have shown that RMS and mean squared errors don't really correlate well with human perception. The noise level could be high, but we may still be able to perceive the details and the sharpness of the objects. But if you blur the edges, then you may not like it, even if the RMS is low. So these measures of error and quality that I showed earlier, they may not always agree with human perception. So that's why there are some measures related to perception. And you have to check with some comparative analysis as to whether the measure that you propose agrees with visual perception as computed in some numerical manner from a number of observers, not just one person. So visual inspection and analysis of the results by qualified users or experts in the domain of application is important. A radiologist is the one who will decide if my image processing method is suitable for mammograms. Not a cardiologist, not me, not somebody else. So here are some images, the test image with noise and 3x3 mean filter, 3x3 median filter, 5x5 mean, 5x5 median. So these two are median filters. These are mean filters. Clearly you can see blurring of edges, especially when the window is large. Compared to that, even compared to the noisy image, this is very blurry. Noise has been reduced. Yes, this is smooth. But the edges are blurred. Look at the median output. The edges are sharp. There is a little bit of blurring here. But the corners have been clipped. So there is shape distortion. This is not a rectangle anymore. And those small little triangles there, they're all gone. When you take the median over a big window, these are smaller than half of 5x5. So they're gone. So if you apply the median filter with a big window, calcifications may disappear from the mammogram. So we need to know the limitations of these. So that's why I have used these synthesized images. They were not designed specifically, but these artifacts have happened here anyway, and you can clearly see that. You may not be able to perceive that in a real image. This is with Poisson noise. The median filter works a little better. The RMS values are given here. I won't read that. They're just numbers. So we have shown with different types of noise, with speckle noise and so on. But the best illustration perhaps is with the salt and pepper noise, where mean filter fails with a small window. Larger window, the noise is reduced, but very blurry result. The median has done better, but again, the small objects are gone. But this heavy noise here, with a density of 0.1, salt and pepper, most of that has been removed. So you need to know something about the image as to what is the smallest object of interest so that you can design an appropriate filter and window. These are histograms of the test images with different types of noise. This is the original, very separated values of different objects. So a bunch of delta function kind of impulses in the histogram. When you add Gaussian noise, we get this. It's all positive. The pixel values are all positive, so you don't have the other side of the Gaussian. Poisson noise and speckle noise. It's a little difficult looking at the histograms to judge what kind of noise it is. I thought we could perhaps see some difference, but it's not so, except in the Gaussian case. So here are some real images. These are test images from the time image processing started. Way back in the 70s and 80s, there were not many databases of public images, or not many people had digital images or the facility to scan printed images. At IISc, I joined the Indian Institute of Science in 1976. I took a course from Professor G. Krishna on digital image processing, and we had a lab where there was a scanner. You will laugh at this, but it was very interesting and innovative, using what is available to scan prints of paper or photographic prints. The print would be mounted on the drum of a lathe machine, you know, the wood turning or machine turning lathe. It was mounted there, and there was a laser source, and the lathe was run. And as the drum rotates, the one row of the image or column, whichever way you see, is scanned. The laser is fixed, and then it is translated. The stage is translated, and you scan. So as the drum goes, you get sort of a helical scan, but the picture is smaller than the circumference of the drum. Yeah, so you get these scan lines. And if you wanted to scan at transparency, there was a hole cut in that drum, and you would mount that, and you had to have a laser beam somehow else. You need to get the beam going through the film. But mostly we were doing prints at that time. So that was done in 1976 and 77. So these images, Pepper and Lena and a few others, were created in which university? There's a reference somewhere. And a database was created. So many research papers use these images. These are also in color. But nowadays, people are getting tired of this, so we need to have other examples. I'm replacing them with other images. And we have other real images too. But there is a little bit of history to these images. So that's the original, and Gaussian noise. You can see the noise there. I hope you can see from the back too. The effect of noise, mean 3x3, 5x5, median, and the median is okay. Not here. The mean is not bad. There is a little bit of blurring at the edges. It's not so obvious with the real image as with the test image. So again, different types of noise. I'll skip to the salt and pepper. This is where the median works really well. The mean fails and the median works. The others, it's a little difficult to see. This is Poisson noise, mean, median. Mean may be better here. 11.12. 3x3 mean, RMS is 11.22. Median is 8.56, but to me this looks better. It depends on your perception. The median filter actually is an order statistic filter. Order statistic filters are a different category of filtering signals and 1D or multiple dimensional signals, where you take a population of your values of the signal or image using a certain neighborhood or window, and typically you take an odd number and you rank order them minimum to maximum, and the ith entry in the list is the output of the ith order statistic filter. That's all. The min filter is the minimum, that's the first one in the list. Max is the last one when they are rank ordered. So the min will help in removing isolated bright spots, the salt noise that will be at the end of the list. And the max will remove isolated dark spots or pepper noise, which is at the opposite end. You select if you select the max. The median is in the middle. If you combine the min and max, you can remove both salt and pepper noise. The median is the entry in the middle, as you saw already. And then there is the alpha trim mean filter, which gives you flexibility, where the mean of a reduced list, you don't average all of the values in that list. Some could be corrupted by noise substantially, and they'll be at the ends of this list. So you want to take only the values in the middle of that list. So you throw away a few values at the beginning and end of that list, very small values and very large values. And the median is giving an approximation of the center of that distribution. And now you say, instead of taking one value only, I'll take a few values in the middle and average them. So it's a combination of the median and the mean filter, but not indiscriminate mean, not averaging everything. So it says you reject the first alpha and the last alpha, alpha being a percentage between 0 and 50%. Outliers are rejected. If alpha is close to 0.5, almost the whole list is rejected except the middle one, which is the median. So you tend towards the median. The output is close to or equal to that of the median. So if you use alpha equal to 0.4, 0.3, depending upon how many pixels you have in that population, the window that you have chosen, the mean of the trimmed list provides a compromise between the mean and the median. So that's one of the order statistic filters that is flexible. Now there is another filter called L filter. You have the ordered list and you give weights to all of them. The weights should add to 1 so that there is some kind of averaging. But you could apply different weights. You could do even a sort of convolution if you want. So it's a weighted combination of all of the elements, and using appropriate weights, you can get all of the filters that we have seen so far in this section. So selecting a window of pixels and rank ordering them and performing these operations will help in reducing different types of noise. Okay? Any questions or comments on this part?
These days we don't see, researchers, students, to say, they don't see the images, but they read the CSV files.
You're okay with 30 minutes more, or are you tired? Tired, and you don't want to say that. 15 minutes. Okay, let's go for 15 minutes. I'll stop at 5:15. As I said, the initial plan was for me to give 40 hours of lectures, and I have signed that document, so I'll talk for 40 hours. Otherwise, GIAN will not invite me again. Oh, it is being recorded, so I should be careful.
That's okay, sir.
No, I didn't say anything bad. So frequency domain filters now. All of the filters we saw so far were in the space domain using pixel values. But we talked about low pass, high pass, and all that. And typically these filters, low pass, high pass, are designed and applied in the frequency domain, where low and high mean frequency. So let's see some frequency domain filters. So most images of natural entities and natural scenery vary slowly and smoothly across space. And they don't have sharp edges. There could be some, but this is not natural. This is a machine-made or man-made object. But if you go outside and take a picture, yes, there are trees with some edges, but overall, there is some smoothness. Most of these images have a large portion of the energy concentrated around the DC, UV equal to 0, 0. Uncorrelated random noise fields have uniform, flat, or white noise. Their spectra will be constant. So the SNR of a noisy natural image is not constant across the frequency range. The SNR could be high in the DC and low frequency area and could be poor in the high frequency area. Noise is constant, signal is high there and it becomes low. So signal becomes low in the higher frequency zone, noise remains the same. Note that noise is existing right across the entire spectrum. So the low frequency region, middle frequency also have noise. So when you do low pass filtering and remove high frequency, the noise in the low and middle range will be there in the output. They are not removed. So to achieve some smoothing and removal of high frequency noise, you can apply a low pass filter, remove or suppress high frequency components. But removing high frequency components along with noise, you lose some desired image components which are related to edges and fine detail, fine texture. So there is always some loss. You reduce noise, but you also lose sharpness and fine details. Noise components in the low frequency pass band will continue to exist in the image. So what is the procedure? You compute the 2D Fourier transform, FKL, design an appropriate 2D filter transfer function, HKL. And typically you would want this to be symmetric. Obtain, and most of the cases isotropic too. Obtain the filter image, GKL is HKL times SKL. You multiply point by point in the frequency domain. And you have to take care of centering. Is the spectrum of the image centered with DC in the middle? If you did that, then the filter function HKL must also have its DC response in the middle. That's how you normally specify filter functions. But the FFT of the image will not give you the centered spectrum. So you have to center it or shift it. So usually HKL is real, affecting only the magnitude of the input spectrum. You don't change the phase. If you change the phase, the output could be affected in manners that are hard to predict and distorted. With real valued images, HKL should maintain conjugate symmetry. So the filter function has to be symmetric. The input image is real, its Fourier transform has conjugate symmetry. So HKL must be conjugate symmetric, but it is real, so it will be symmetric. But typically one uses isotropic filters, so radially it is the same. FKL may have to be centered or folded depending upon how you have created HKL in your software. Compute the inverse Fourier transform. If FKL was folded, then it must be unfolded and then do the inverse transformation. If it was zero padded, then trim the result and get only that portion that has the image. So that's the FFT-based processing or DFT-based processing. So removing high-frequency noise, you use low-pass filters. The assumption typically made is noise is additive. Fourier components of the original image past a certain frequency cutoff are negligible. So you say, I'm going to cut there. But there will be some loss of some frequency components of the signal. The so-called ideal low-pass filter has a sharp cutoff. It's a rectangle or gate function. Your low frequency components up to some frequency and then gain is 0. Gain is 1 and then 0. So that sharp transition causes problems. When you have such a sharp transition and one of the signals is band limited, its Fourier transform cannot be limited. If you have a band-limited function, it is not time-limited or space-limited. If it is space-limited, it is not band-limited in the frequency domain. Like the rectangle function is space-limited, but its Fourier transform sinc function goes forever. Right? And if it is an impulse in the frequency domain, it is band-limited, but its inverse Fourier transform is a constant forever, all space. The ideal low-pass filter is defined to have gain 1 up to some frequency d0, where duv is the distance from the origin, or square root of u square plus v square, uv being the horizontal and vertical frequency coordinates in the Fourier space. So d0 is the cutoff frequency. But the ideal filter creates problems. The name ideal means there is a sharp transition, pass band, stop band. But that, it might work well in time domain applications, and it is called ideal filter there too. But in image processing rather, it creates serious problems. So it is not ideal or suitable here. But anyway, the filter function looks like this, a circle. That is, DC is here up to certain frequency, you pass, and after that, the gain is 0. That's a Butterworth low-pass filter. We will get to that later. If you take a section, the ideal filter is that. Sorry, it's a little difficult to see that in this plot, but there is a line there. That's the ideal filter up to 0.2, and after that, the gain is 0. The Butterworth filter has a smooth transition, monotonically decreasing function. And this is 0.5 normalized frequency, half the sampling rate. 0 and minus 0.5. A glaring artifact, because of the ideal filter, is echoes of edges. Because the inverse Fourier transform of a rectangle is a sinc function. Sinc function has side lobes, positive and negative. Multiplication in the frequency domain with the rectangle causes convolution in the image domain with the sinc function. A sinc function, when you convolve, it gives you positive and negative sort of reverberations or echoes. And one edge will cause multiple artifacts, positive and negative edges. So the inverse Fourier transform, if it is a sorry, we are not using rectangle, we are using a circle, so it is a Bessel function. A section is a rectangle. But the 2D function is a circle, so it is a Bessel function, similar positive, negative side lobes. So this is known as the ringing artifact. The ripples or lobes of the Bessel function lead to echoes of strong edges and objects and causes this ringing artifact. So you see these patches. The edge here appears, and that edge is echoing here, and it goes all over. And they all interact and mess up the image. So this is the original with noise and ideal filter. That is the Butterworth. We'll come to that later. So can you see that? The patches here, and see the triangle here, and bright edge, and a dark line there, which is the ringing of that. And there will be a similar one here, a negative one coming here, which will reduce the intensity inside. Some of that may not be clearly visible. If you zoom it and look at this image on your screen, you may see better. So this is the spectrum of the shapes test image. This is with noise added. It's a little hard to see the difference. The Butterworth low-pass filter is defined in this manner. Gonzalez and Woods have this definition. In 1D, it is defined in a similar manner, but not exactly the same. What you want in a good filter is a maximally flat response in the pass band and suppression in the stop band and a transition that is as fast as possible between the pass and stop bands, but you want a monotonically decreasing function. Sharp changes in such a function will cause repercussions in the other domain, in the image domain, that are not desirable. So you want this function to be smooth, and the Butterworth function is one that has a maximally flat response in the passband, and it is monotonically decreasing. It is defined as this 1 over 1 plus a scale factor, the frequency, which is defined as DUV, distance from 0, square root of u square plus v square, divided by d naught, that's the cutoff frequency, to the power of 2n, where n is the order of the filter. If you refer to my 1D signal processing book that was being passed around, there is more information about this in the 1D case and how to derive it. So for a Butterworth filter of order n, the first 2n minus 1 derivatives of the squared magnitude response are 0 at omega at equal to, or frequency equal to 0. We don't use omega, but that's in 1D. So that is what is meant by maximally flat. Not only the value, but its derivative and so on. How many orders of derivative depends on n. So the larger the n, the flatter the response in the passband, and faster the transition from the passband to the stop band. So those are the properties of this filter. And it is monotonic in the passband and stop band, and monotonic in the transition too. So DUV is square root of u square plus v square. D naught is half power cutoff frequency. The gain is equal to 1 over root 2 at the cutoff frequency. Or the power is 1 over 2. So here is an example. This image of a clock in our lab. We took it using an old video camera, digitized it, a lot of noise, and the spectrum of the image. And this hand, you see the directional component there. There are horizontal, vertical edges giving that. I also zero padded, so which has caused some additional artifacts there. So this is with ideal filtering. You have these ringing artifacts, and this is with the Butterworth filter that does not have any ringing artifacts. There is smoothing. The filtered images are smooth, which is what you want. How much smoothing? You design an appropriate filter with appropriate cutoff and order of the Butterworth filter. This is already blurry, and there is more filtering, but the ideal filter introduces these artifacts. The Butterworth is free of that artifact. And go back, and here also, the Butterworth filter is free of the ringing artifact. Noise has been suppressed to some extent. Not all the noise is removed, because noise in the low frequency and intermediate frequency will stay. So there is some noise here. It's not like that. And sometimes it may introduce some false texture. You may think it is, or you will perceive some texture, but that is false. That is filtered noise. So that's the difference between the two filters. There could be some periodic artifacts, sometimes with grid lines, as I mentioned. And if you have a picture that is drawn on some sort of a graph paper, then there are these vertical and horizontal lines. Periodic components give rise to impulse-like periodic concentrations of energy in the Fourier spectra. Periodicity means there is a pattern and it is repeated, and repetition is convolution with the delta function. You repeat the same thing. So when you have some pattern that is repeating, it implies that there is a basic pattern or motif, and that has been convolved with the delta function that has a number of delta functions. Periodic or not, there are repetitions. And at every delta function, this pattern is copied. And if the delta function train is periodic, then you got a periodic pattern. So if you have grid lines that are periodic, then there will be impulses in the Fourier domain at the inverse of that spacing, which is the frequency. So this facilitates removal of periodic artifacts if you know what the period is, or you examine the spectrum of the distorted image, and if you see points of high intensity, that indicates periodic artifact, and that should be visible in the image too. So you remove these artifacts. How do you remove is a question. I was discussing with one of you earlier about this, and if you just use a notch filter and set those values to 0, you will have artifacts because the original spectrum didn't have 0 there. You can assume the spectrum is continuous, and at the location of these spikes or impulses, you average and set it to some values in between that will make the spectrum smooth in that range. Or apply some sort of filter that does not cause large discontinuities in the spectrum. So removing the artifactual components lead to the loss of frequency components of the desired image. They were added, but the image has some energy there. You need to preserve that and remove only the artifact. That is a bit of a challenge. So here is an image of a part of an image of a mammographic phantom with calcifications. There are various phantoms for various parts of the body and different imaging modalities. A phantom is a test object that is created by various companies. They manufacture and sell them. You test your imaging facility with that, imaging system with that. And there could be some grids there, and you want to make sure that the high frequency grids will still be visible with good resolution in the image that you acquire. And calcifications such as these fine spots should be clearly visible. You measure the contrast and so on. So for each type, each body system or part and each imaging system, there are various phantoms. I asked Dr. Hahn, my colleague in nuclear medicine, to take a picture of this phantom with and without the grid moving properly. The grid has to move during the X-ray image acquisition procedure to get a smooth image, to reduce scattered photons and scattered noise due to scattered photons. But if it doesn't move, you get these lines. Those are the grid lines. And these bright spots are the calcification simulating material in the phantom. This is the spectrum of the image. The lines are horizontal with some spacing. So horizontally, each line is a constant. So it doesn't have any component in the horizontal frequency, but in the vertical frequency, there is that variation, and you get these spikes. Periodic, there is DC, of course, and then that, and so on. So when you see that, you say, oh, there is some artifact, clearly. There is also smearing this way, which could be due to aliasing or could be due to the fact that I'm using a finite window to compute the Fourier transform. Otherwise, you should only see these spikes. So to remove that, I thought, well, I'll just punch out those spikes and set to 0. That's not a good filter, but these are the regions I blocked out. A very bad filter. But I want to show you the artifacts also that are caused by the filter. So all these blacked out regions are where my filter was set to 0. And this is the output I got, which is, the grid lines are not there, but you see the artifacts because there is discontinuity here. So a better filter would have been to, if you take a section here, so there is some, let's say there is some spectrum, and suddenly there is this spike, and then it goes on, and then there is a spike. I set it to 0 and totally eliminated that, and then the spectrum goes like that and goes to 0 and comes up again and then goes to 0. And that discontinuity gives rise to artifacts in the image domain after inverse transformation. What I should have done would be something like this. Keep all of that, and where there is a spike, apply some interpolation, and then keep the rest there. And then where there's a spike, apply interpolation, fill the gap, and make it continuous, make it smooth. Assume that the spectrum is continuous, which may or may not be true, but there should be some continuity. Are those the real values? I don't know. I don't know what was there before the noise. In any case, this is what I got, which is not the best result, but I want to show what works and what doesn't work also. If you want to design a better filter, you could try something like that, to interpolate and fill the gaps. This is the original image if the grid has worked properly. Now, you wouldn't take such with and without grid movement with patients, of course. You can't do that twice. So with the phantom, we could do such a thing. So this is how it should have been, and its spectrum. The filtered one is not like that. All right, we will stop here. It's a little past 5:15. Matrix representation of image processing involves some more mathematics. Of course, there's a lot of mathematics. And we will see some optimization procedures based on matrix representation. We will see that tomorrow. Are there any questions or any comments? Am I clear, and are you following the presentation and discussions? I've had a couple of you come and talk about other things, but is this clear? Please do go through the notes, because I've skipped some parts, and in order to really get all the details, you should take each equation and work through. Not today, not tomorrow. It's a nice place. Go to the beach and walk around. But later on, please go through that, and that procedure will help when you design your own research algorithms. That experience helps. And you could also create phantoms and test pictures and write your programs and work with them before applying your methods to real-life images, because these phantom images will show you what is good and what is bad, what is working and what is not working, what are the artifacts that are removed and what are you introducing by your technique of whatever filtering you're doing. Whereas when you apply it to a real image that is so complex, it will be hard to see such details. Any comments, questions? All right, thank you.